Hi, in this tutorial, you will learn how to solve problems involving projectiles that are launched at an angle. So it looks something like this. And at this point, I just wanted to point out first the key differences between a horizontally launched projectile and one that is launched at an angle. The reason being is because if you just came from a tutorial teaching you horizontally launched projectile, you may just carry over some misconceptions as you transition to case 2 projectile. So just to distinguish the two, first, you have to know that in horizontally launched projectile that you might have dealt with earlier, the velocity given in the problem is v sub x, so velocity along x, because it's horizontally launched. But be careful, because when you are dealing with projectiles that are launched at an angle, the velocity that they will give in the problems is usually just the actual v, meaning to say the velocity in the actual trajectory, which points this way. However, you can solve, and you may need to solve for the v sub x, or horizontal component of velocity, and v sub y, or vertical component of velocity, using that v, or velocity value. So that's it. You're just going to use trigonometric equations. Another difference is that the initial vertical velocity for case 1 projectile is always 0 upon launch, which is obvious because the initial velocity is projected horizontally for case 1, so the vertical velocity initial is 0 meters per second. However, for case 2 projectile, it's launched at an angle, so meaning to say the initial vertical velocity is not 0 upon launch. There has to be a vertical velocity to cause that upward motion, so that is case 2 projectile. And then, next, just a quick recall, the general problem-solving steps when dealing with projectile problems. Make sure that you have an accurate representation of the scenario. No need to be artistic, just make sure it's accurate so you won't go wrong with the analysis. And then write down the given variables. And then, of course, identify the required to find and the missing variable. Again, the missing variable is the variable that is not known in the problem, but you're also not solving for it. Next, solve for the RTF by choosing the right equation. And then whenever you seem to lack known variables in one component, let's say x, then you work on the other component first, which is y. And then evaluate your answer. So you ask yourself, is the answer reasonable? Is it too high? Is it too low? That's for you to be able to get a chance to review your solution before boxing in your final or quote-unquote final answer. And then next, again, these are the equations that we're going to be dealing with. And then these are also the variables that you have to treat as your best friends when dealing with projectile problems. We're going to go through all these things during the actual problem, which is this. So a batter hits a baseball, which leaves the bat at a speed of 35.0 meters per second at an angle theta equals 54.3 degrees. For letter A, you have to determine the position and the velocity of the ball at 1.50 seconds. You have a lot of required to find in here. So what we're gonna do is, I'm not gonna read the whole thing. Let's deal with it one by one. So let's start with letter A first. Determine the position and velocity of the ball at 1.50 seconds. So this is how we can visualize the scenario. So as you can see, the baseball is actually launched at some height above the ground, but take note that that height is actually negligible, meaning to say it's too small, you can disregard it, and just really think of the baseball to be following a trajectory where the starting point and end points are just equally high. So don't be bothered by this additional height. And then next, so this is how we can visualize like the front view of the scenario. So this is the velocity that is given in the problem. Let's write it down. So according to the problem, initial velocity is 35.0 meters per second, and it makes a 54.3 degree angle with the horizontal. And then next, take note, however, that when you are given initial velocity in case 2 projectile, that is neither the v sub x nor v sub y. That's why I'm writing it in the middle of this table, not just on x or y. And take note that if you know this, you can solve for v sub x and v sub y in your problem. And that is important because v sub x and v sub y can be readily plugged in our kinematic equation. So again, in case 2 projectile, your first impulse should be to determine v sub x and v sub y whenever you are given just the initial velocity. So again, v sub x is represented by this, and you can solve for it using v naught cosine theta, we'll put it here because we'll solve for it in a short while. And then the vertical velocity, initial vertical velocity to be specific, is also gonna be required to find because we need it. We're probably gonna need it afterwards. And then the formula for that is V naught sine theta. So meaning to say you just plug in the angle so as well as the initial velocity to know the initial vertical velocity, but we're gonna solve for that afterwards. So again, dealing with question A, determine the position and velocity of the ball at 1.50 seconds. But before doing that, let's write down some of the known variables exclusive to case A, which is, or to part A, which is time is 1.50 seconds, meaning to say this is our concern for part A of this problem. We don't really know when is 1.50 seconds in the trajectory, but maybe this is around at this point, just a guess, just so we could visualize what's happening in the problem. So the concern here is the velocity as well as the position of the ball at 1.50 seconds. And this vector arrow could represent the velocity after 1.50 seconds. And then d sub x is also required to find. So d sub y is also required to find. Why? Because it says determine the position. And take note that the position of the projectile would be its displacement along x as well as the displacement along y. Meaning to say, guys, we need to know how far the ball has traveled horizontally. But because this is a two-dimensional motion, we also need to know how far it has traveled vertically, that's the d sub y, after this time that's given to us, 1.50 seconds. That's why when you're asked for the position of a projectile, you're basically just gonna give d sub x and d sub y as your answers. And whatever you get for those values, they will tell you exactly, like they will act like coordinate points and they can pinpoint exactly where is the ball now at 1.50 seconds. Next, another given, the velocity of the ball. So I'm gonna write v sub t equals 1.50 seconds. If you just wanna write a v, which could represent final velocity, it's also okay. I'm just writing a subscript t equals 1.50 seconds just so I don't get confused afterwards, and I'm sure that this velocity refers to the velocity once the time is 1.50 seconds. So that's the required to find for this part, velocity of the ball. Next, take note that if you are being asked for the velocity at 1.50 seconds, you also need to know the vertical velocity at 1.50 seconds because we're gonna use some trigonometric functions for you to like solve for these diagonal, not exactly this curve velocity to solve for this velocity. And then next, we also know that along y-axis, the acceleration is negative 9.8 meters per second squared. So let's look at our variables if we've listed down everything that we could list. So d sub y is required to find. Acceleration along y is known. The time has been accounted for. It's been listed here. We want 1.50 seconds as the time of consideration. V naught y is actually here. We can solve for it right away. V sub y, or final velocity, specifically at 1.50 seconds, is also another required to find because it's needed for the actual velocity at 1.50 seconds. Next. Okay, so before we proceed to the actual required to find, I would like us to solve for v sub x and v naught y because they can readily be solved for using these equations. So v sub x is, v sub y rather, is just v naught sine theta, and then v naught, or initial velocity, is 35.0 meters per second. Theta is the one, or the angle that it makes with respect to the horizontal, and that's 54.3 degrees, and you're supposed to get 28.4 meters per second for your initial vertical velocity. Meaning to say, upon launch, the initial vertical velocity of the baseball is actually 28.4 meters per second. And then how about the horizontal component of the ball's velocity? So again, that is v cosine theta. So that's v sub x equals 35.0 meters per second. It's this. And then cosine 54.3 degrees. And you're gonna get 20.4 meters per second. You might be getting confused, like, Miss, why are you writing v naught cosine theta here, but here it's v cosine theta? Well, this is the generic version, or like the generalized way of writing the relationship between v sub x and the actual v. In this one, I just made it a bit more specific by actually writing that we are talking about the initial velocity, which is this. But yeah, It's not strictly required for x component because v sub x is actually constant. So that's our v sub x. Next, let's try solving for the position because now what we have done so far is that we resolved the initial velocity into its x and y component. So this is the x component of our velocity, and this is the y component of our initial velocity. Useful information because they can be readily plugged in to our kinematic equations. Now, solving for the position, again, the position is given by d sub x and d sub y because knowing the displacements along x and y will tell us where the ball is after 1.50 seconds. So, solving for the position at 1.50 seconds for x-axis, so we have v sub x equals d sub x over time. Nothing bloody. Always remember that this is our main equation for the x component because this is for constant velocity motion and the velocity along x is constant because gravity isn't acting there. It's not bothering the baseball horizontally. Then we cross multiply to isolate d sub x. So we have d sub x equals v sub x times time. Then plug in. So horizontal velocity is 20.4 meters per second, and the time that we're concerned with is 1.50 seconds in the problem. Then cancel seconds. You're supposed to get d sub x equals 30.6 meters in your calculator, which looks reasonable to me for a baseball. 30.6 meters looks sensible as a horizontal displacement that's covered for this kind of sport. Next, so that's our d sub x now. To complete the position of the ball, we need to solve for d sub y. To solve for the position of the ball at 1.50 seconds, we're gonna be looking at d sub y. So in the y-axis, the required to find that we're gonna focus on first is d sub y. Miss, what if you have two required to find? The v sub y is also labeled as required to find. Definitely, we can solve for two required to find at the same time. So what we're gonna do is to think of v sub y as missing variable first because we don't want to deal with it yet. The required to find we're aiming for right now is d sub y to get the position of the ball. So we're gonna treat v sub y as missing variable for now, meaning to say we don't want to solve for it yet and we also don't know its value. So, and then after that, because we've accounted for all these variables, d sub y is what we want to solve for. Acceleration along y, we know it, and then time is also 1.50 seconds. Initial vertical velocity is known, and then v sub y is the missing variable. So with that, we need to pick the equation which does not contain the missing variable, which is v sub y, or final vertical velocity. And that is the fourth equation. So again, we're picking this equation because it does not contain the missing variable, which is final vertical velocity, or v sub y. So let's write it down. It's this, and then plug in. So initial vertical velocity is 28.4 meters per second times the time we are concerned with. So that's 1.50 seconds plus sign. And then this is the acceleration due to gravity or a sub y. And then time squared. So that's 1.50 seconds raised to 2. Do not forget to divide this expression by 2 as seen in this part of the equation. Then let's simplify. So cancel the units. That should be canceled. The first part of the equation should give you 42.6 meters. And then you have a minus sign in here because this is a negative value. And then this is 11.025 meters. I'm not yet applying sig-fig rules here because we are just in the middle of the computation. So towards the end, yeah, that's what we're gonna do. Subtract these values. You're supposed to get 31.6 meters as the d sub y. And that looks sensible. Definitely, a baseball can cover 31.6 meters vertical displacement, especially if it is hit strongly by the batter. So this makes sense. The units also make sense. In terms of the significant figures, in subtraction or addition, we follow the given with the least number of decimal places. So this has 3 decimal places. And then this has 1 decimal place. So this has less decimal place than this one. So the final answer should have 1 decimal place as well. Again, for the significant figures rule of subtraction or addition, you follow the given with the least number or less number of decimal places. Okay? So 1 decimal place, 1 decimal place. So that's our final answer for the position of the ball. Again, if you're wondering, so what's the final answer now, miss? The position of the ball is 30.6 meters along the x-axis and then 31.6 meters along the vertical axis. So that would be, if this is your scenario, that means to say that the ball has covered 30.6 meters horizontally, and then let's pretend this is 30.6 meters up to this point. And then for the height of the ball, it has covered 31.6 meters. So whatever will come out of that, maybe it's here. We don't really know exactly where, but yeah, that's the idea behind it. Its position is determined by both the x and y displacements, or horizontal and vertical displacements. So that's it. Again, that's after 1.50 seconds. Now let's erase this board. At this point, we're gonna solve for the velocity of the ball at 1.50 seconds. So again, that is v sub t equals 1.50 seconds, or velocity when the time is 1.50 seconds that we're concerned with. We can represent that as this diagonal vector because when you say v, it's the velocity in the actual trajectory, the one that is curved actually. So you can use this vector arrow to represent that, and then so that's the required to find, specifically at 1.50 seconds, okay? And then it has a horizontal component, which is 20.4 meters per second, and then it has a vertical component that we actually don't know. Wait, miss, why are you doing the triangle thing? That is because for you to know the velocity of the ball at 1.50 seconds, you have to know its x and y components first before you can actually solve for it. Because the equations that can give us proper answers are exclusively used for x or y axis. So if you know x and y, you can determine v from there. Okay? So let's solve first for v sub y because we don't have a problem with v sub x. It's 20.4 meters per second, and v sub x is constant throughout the trajectory. So it's still true, it's still the v sub x after 1.50 seconds. But for v sub y, we need to solve for it first. And then, yeah, be careful, just a reminder, do not use the theta 54.3 in here because this one is upon launch, but this illustration here is concerned with 1.50 seconds, not the launching angle. So do not be tempted to use 54.3 for this particular part because it's not necessarily the angle when time is 1.50 seconds, okay? So going forward, again, we're solving for v sub y for us to eventually solve for v, which is the main required to find. Now, let's see first how our variables are going. So first, our d sub y is actually known. It's 31.6. Of course, acceleration along y is known. And then time, again, we're concerned with 1.50 seconds based on the problem. Initial vertical velocity is still true at this point. And then final vertical velocity is the required to find. Now, we normally pick the equation that does not contain the missing variable. So you might be thinking, miss, we don't have a missing variable, we have everything. That means to say you can choose any equation as long as it contains the required to find, which is the final vertical velocity. But I have a tip, and what I believe is the best thing to do in this case is to pick an equation which, of course, contains the required to find final vertical velocity. But at the same time, you should avoid this value, d sub y, because you just solved for it. So if there's any error associated with your d sub y calculation, then your answer might probably be inaccurate for v sub y as well. So yeah, the tip is to treat d sub y as a missing variable instead of considering it as a given. And if you do that, you're gonna have to pick an equation which does not contain displacement, and it's this one. So let's choose that one. So solving for v sub y, or final vertical velocity when time is 1.50 seconds, we're picking this equation. Again, we're picking this because it contains the vertical velocity or final vertical velocity, and we're also avoiding the d sub y, which is something that you only solve for. Okay? Then plug in. So initial vertical velocity is 28.4 meters per second plus acceleration, and then this is time. If you simplify that, you're gonna get this. And finally, if you subtract them, this will be your final answer. So 13.7 meters per second for v sub y. So what? Okay, at this point, you know you wanna know velocity, And you need v sub x and v sub y for that. So now we already know our final vertical velocity to be 13.7 meters per second. And you can solve for v at this point. And then another additional point, you may also use the equation v sub y equals v naught y minus gt. It's actually just the same as this one. I just wanted to show this because you can see some physics textbooks using this kind of way of expressing this equation. Just be careful because the g here is actually positive. So meaning to say, it's going to be v naught y minus 9.8 meters per second times time. So basically, the equation is just showing you that whatever is your initial vertical velocity, it's just gonna be decreasing by 9.8 meters per second within a certain amount of time that you are considering in the problem. So that's actually it. But it's actually essentially similar to this. So going forward, again, we can now solve for our velocity because we know v sub y and v sub x. So let's do it. So first thing, a velocity has magnitude and direction. So solving for velocity, we can use the Pythagorean theorem. Miss why? Simply because you have a right triangle here, and the velocity is technically the hypotenuse, and your two other legs are known in the problem. So you can use the Pythagorean theorem. And to isolate c, because you have an exponent to right here, get the square root of both sides of this equation, and you're gonna have c equals square root of a squared plus b squared. But I don't like this expression because this is very mathematical. I want the physics version where I'm basically replacing a and b with v sub x and v sub y because those are the ones that we have in the actual vector representation. And then c is actually the hypotenuse, which is actually the velocity that we are solving for. Next, plug in the given. So v sub x is 20.4, v sub y is 13.7, and if you do this in your calculator, you're supposed to get 24.6 meters per second for your velocity. So that looks reasonable to me because the initial velocity is 35.0 meters per second, but then going up, so in here, it's 35.0 meters per second, but then after 1.50 seconds, the velocity should be slower because of the effects of gravity, the opposing effects of gravity. So this lower value than 35 makes sense. And then next, of course, our velocity is not complete without the direction. So for the direction, you just do determine this theta. Because this is a right triangle, then this theta can be conveniently solved. So we can use, we can consider this as our opposite side, v sub y. And then our adjacent side in here would be our v sub x. So you can use tangent theta equals opposite over adjacent. And then you can replace opposite with v sub y because based on this illustration, opposite side is the v sub y. And then adjacent is the v sub x. So that's how we came up with this. And then, take note, you need to cancel tangent because you're just solving for theta. And to do that, just multiply both sides of the equation by arctangent because if you do that, you can cancel this tangent expression. And of course, you're going to distribute this to the right side of the equation as well. So that will give you theta equals arctangent times v sub y over v sub x. You might see some other references using tangent raised to negative 1. It's just the same as arctangent. Okay? So, plug in. Our v sub y at 1.5 seconds is 13.7 meters per second, while v sub x is constant ever since it was launched, so it's still 20.4 meters per second. Okay? Then, in the calculator, if you do that, you're gonna get 33.9 degrees above the positive x-axis. So, if you're wondering, Miss, how did you do that in the calculator? Or first, why is it above the positive x-axis? So, if this is your vector representation, this is the vector you're describing, right? The one that is considered as the v. If you imagine the what do you call this in the Cartesian plane? Yeah, the horizontal axis of your Cartesian plane. If this is your velocity vector, the theta that we solve is actually above the x-axis of our Cartesian plane. So it's 33.9 degrees above the positive x-axis. Miss, I don't know how to do this in my calculator. What's this? There's arctan and everything. It's so confusing. So what you need to do in your calculator to execute this operation is to press 13.7, division sign, and then 20.4, then press equal sign, and then press shift. For other calculators, it's second function or second F. and then press tangent, press equal sign, then you're supposed to get 33.9 degrees. And just add the expression above the positive x-axis or below the positive x-axis, depending on the case. So again, that's our final answer for the velocity of the ball at 1.50 seconds. So it is 24.6 meters per second, 33.9 degrees above the positive x-axis. Again, when you are solving for velocity, make sure there is a magnitude as well as direction, because velocity is a vector quantity. Okay? At this point, we're going to solve for the maximum height reached by the ball and the time when the ball reaches this highest point. So first thing, considering that we're no longer concerned with this 1.50 seconds thing, we need to update the given variables in our table. So the first concern is that we would like to solve for the maximum height, and then because of that, we can no longer say that d sub y, or vertical displacement, is 31.6 meters. We cannot use this as a given because this displacement is concerned with what happens at 1.50 seconds, but at this point, we're concerned with the time when the ball reaches the maximum height. So the d sub y here actually becomes the required to find. So d sub y, again, is the vertical displacement when the ball reaches its maximum height. Now, take note that you can also label this as y sub max. I know some teachers and textbook references that use y sub max to represent the maximum height in terms of the abbreviation. So y sub max is read as maximum height because y refers to the vertical axis, of course. So that's all required to find. You can also stick with d sub y as long as you are aware the whole time that you are referring to the vertical displacement considered to be the maximum height of the ball or the highest point of the ball. And then take note that v sub y, or final vertical velocity, is no longer 13.7 meters per second because earlier, this 13.7 meters per second is the vertical velocity when the ball has traveled 1.50 seconds. But at this point, the vertical velocity of the ball should be considered as 0 meters per second, or the final vertical velocity is 0 meters per second, because when a projectile reaches its maximum height, take note that the vertical velocity actually becomes 0 because going up, the object or the projectile will actually continue decreasing its vertical velocity by 9.8 meters per second until the vertical velocity becomes 0. That's why the projectile actually comes to a momentary stop when it gets to the maximum height or to the highest point. So that is because the vertical velocity at the highest point or the peak height is 0 meters per second due to the opposing effects of gravity. So always remember this for projectiles getting to their highest point. Always remember that the vertical velocity is 0 meters per second. And we're gonna consider this as the final vertical velocity because our point of consideration in this particular part of the problem is the time, from the time when the ball is launched up to the maximum height. So this is our concern in terms of analysis. So the starting or initial vertical velocity here would still be 28.4 meters per second, but the final vertical velocity we're gonna be considering is the one at the maximum height. And again, the vertical velocity at the maximum height is 0 meters per second. And then for acceleration along y, of course, it's still negative 9.8 meters per second squared. Wait, miss, it stops at the maximum height, right? So why is the acceleration still negative 9.8? Isn't it supposed to be 0? That is a common misconception. So students do think that because the object stops at its maximum height, the acceleration should be 0. No, definitely, the gravitational force is still affecting the object even when it reaches its maximum height. Therefore, the acceleration due to gravity is still negative 9.8 meters per second squared. So gravity is still pulling it down. That's the reason why after stopping at the maximum height, it will still go back down. That is because while vertical velocity at the top of the trajectory is 0, the acceleration is still negative 9.8 meters per second squared. So in fact, going back down, the object will pick up a vertical velocity of 9.8 meters per second squared. Okay? But let me clean that board. Okay, so going forward. Okay, and then what else? For the time, we can no longer use time equals 1.50 seconds because as you can recall, this is actually for part A where we are concerned particularly with what happens to the ball when it reaches 1.50 seconds in its trajectory. So this is no longer considered as a given because we don't really know the time when the object reaches its maximum height. Okay, so maybe it's more than 1.50 seconds, or maybe not, right? We don't know. We have no idea. So the time is actually not known in the problem. So let's look at the inventory of our y variables. We don't care about x for now because we're concerned with maximum height, which is a vertical variable. So v naught y is known, okay, based on this. And then d sub y is the target or the required to find. And then final vertical velocity is also known. It's 0 at the maximum height. Acceleration, of course, along y, it's known. And then the time, okay, the time is our missing variable. Okay, so time is our missing variable, meaning to say, we don't know the value of time at the maximum height, but it's also not yet the required to find because right now we're concerned with just the maximum height, okay? So therefore, the missing variable is time. And again, when the missing variable is time, we need to pick the equation that does not contain time because if we do that, we have something to plug in for these variables, and then one of them would be the required to find. That's how it works. So again, you need to pick the equation which does not contain your missing variable. Okay, now let's clean this board and then let's choose that equation. So it's this one. Solving for the maximum height, again, we're picking this equation because it does not contain the missing variable time. And then take note that we can cancel vy squared. Why? Because v sub y, or final vertical velocity, is 0. So you can cancel this. And the equation becomes 0 equals v naught y squared, or initial vertical velocity squared, plus 2ad. Okay, and then we transpose v naught y squared to the left side of the equation because we are aiming to isolate d sub y, that is representing the maximum height. So this equation becomes negative v naught y squared equals 2a sub y d sub y. So that's it. We're not yet done. Again, we're aiming to isolate d sub y, which will give us the maximum height. So we divide both sides of the equation by 2 times a sub y, because that way you can cancel it on the right side of the equation, and that will give us d sub y equals negative v naught y squared over 2ay as our final working equation. The next thing we do is plug in, or substitution. So d sub y would now be negative 28.4 meters per second raised to 2. So again, initial vertical velocity is still 28.4 meters per second. Do not forget to affix the negative sign, and do not ever forget to raise it to the second power. And then on the denominator, we have 2 times the negative 9.8 meters per second squared, acceleration constant. In your calculator, it should give you 41 meters as the d sub y. Okay, so take note that you're going to have a positive answer because negative over negative will give you positive. And then take note that in terms of significant figures, so 28.4 has 3 significant figures, 9.8 has 2 significant figures. So in terms of division, you need to follow the number of significant figures of the given with the least number of sig fig, and that is 2 sig figs, so you have 2 sig figs here as well. We don't consider 2. I don't want to consider it because it's just a constant in the equation. It's not some measured or derived quantity for you to consider it when you are counting the sig figs. So that's it. So 41 meters, and then it makes sense that it's positive because displacement actually comes up as negative if it is measured above the original position of the object. So if your ball started from this point, then that simply means that the 41 meters is above that starting point, which makes sense because 41 meters is here. It's not here underground, right? So this answer makes sense. In terms of magnitude, 41 meters also looks reasonable for the height reached by a baseball, considering that it was actually batted or hit at a high angle. So that's it. Next, what we're gonna solve for at this point is, so again, 41 meters for the maximum height. Now, I'd like us to solve for the time when the ball reaches this highest point. So we know the fact that the ball reached 41 meters for its maximum height. But our next concern is at what time did the ball actually reach this particular height or this maximum height? So at this point, we're not gonna consider time as a missing variable. Okay, what we're gonna do is consider time as the required to find, okay? Specifically, the time when the projectile reaches its maximum height. You can also rewrite time as t sub max rather than just saying t, because it will just keep you focused and not confused that the time that you are solving for is the time at the maximum height. So some teachers would write it like this, T sub max, and that's okay. And then looking at our inventory of known variables along y, so we still know v not y. It still applies. Okay, initial vertical velocity is still this, right? We're just still talking about the same ball. And then d sub y is 41 meters. Okay, so this is the d sub y that applies to what we're solving for, because this is the vertical displacement when the maximum height was reached. And then the time that we're solving for is also the one at the highest point. So it's applicable. Acceleration along y is still given. And then again, the time is the required to find. And then the final vertical velocity is actually still 0. You can still use this because at the maximum height, again, the vertical velocity is considered as 0. What does it mean? It shows that we don't have a missing variable. And if you don't have a missing variable, it means to say you can choose any UAM equation as long as the required to find is present in there. But my tip is to use the equation where you can avoid using a variable that you only solve for. So you only solve for d sub y, right? 41 meters. It's not given in the problem. You just solve for it. So there are any errors associated with it, like rounding errors, or maybe in a practical perspective, if you're taking an exam, your d sub y might be wrong. So you might want to avoid using d sub y. You get the point. So my tip in this case where you don't have a missing variable is just to consider d sub y as a missing variable so you can avoid using it because you only solve for it. What if it's wrong, right? So let's pick an equation which does not contain d sub y, and that is, it's this one. So we're gonna pick this because it does not contain d and we only solve for d. So we want to avoid using that. So that means to say our final working equation would be this, okay? So solving for the time when maximum height was reached, we have this equation, and then we can cancel v sub y because it is 0, okay? So we're gonna have negative v naught y equals ayt y, simply because I transpose v naught y to the left, making it negative. That is because I'm trying to isolate time, okay? So next, we divide both sides of the equation by a sub y because I want to isolate time. So you can cancel a sub y now, and you're gonna have negative v naught y over ay equals time. And then we flip it horizontally because we want the required to find to be on the left side. So you're gonna have t sub max equals negative v naught y over ay. So take note, you can stick with just using t, but in the middle of this computation, derivation, I just put max as a subscript of t, so we don't get confused with it towards the end of this problem. So we plug in the given variable. So initial vertical velocity is still 28.4 meters per second. Do not forget to put a negative sign because that is in the equation. And then acceleration still negative 9.8 meters per second squared. And then in your calculator, you should get 2.9 seconds for the time. So this is the time that the baseball gets to its maximum height. So our guess earlier that 1.50 seconds is here looks reasonable because at the maximum height, it took roughly 3 seconds or 2.9 seconds in here. So meaning to say, we were right with the assumption that 1.50 seconds is somewhere around this part. So that's it. It looks reasonable. I mean, if you imagine a baseball getting or like getting hit, 3 seconds looks reasonable for it to like gets to its maximum height, so it makes sense. The units also seem to cancel properly, so s over 1 over s squared should give you seconds for this one. So that's our final answer for the time reached at the maximum height. At this point, we're gonna solve for the range of the ball. So when you say range, it's just the maximum horizontal displacement that the ball has experienced. And to solve for the range of the ball, I think there are different approaches to doing it, but obviously, we're only concerned with the x-axis now because range is a horizontal displacement. So as you can see, to provide more space for us to solve for, I just removed the y variables, and I just retained the variables that are applicable to the x-axis. So initial velocity would still apply to the x-axis because, this initial velocity is not only for y nor x, so we can use it for this one whenever needed in case. And then t sub max, or the time at the maximum height, is 2.9 seconds. Remember that from the previous part of the problem. So it still applies because whatever time you are solving for at any point in the problem, it applies both to x and y components. So solving for the range of the ball, we can use v sub x equals d sub x over time because this is the equation that we have for the horizontal component. It's for constant velocity. And then we actually need to rewrite it or do cross multiplication for us to isolate d sub x. And we should get d sub x equals v sub x times time. Take note that you can also replace d sub x with r or range at this point in case you don't want to be confused or you don't want to get lost that you're solving for range. But d sub x will also do because it still refers to horizontal displacement. And then take note, if the time that the ball reaches the maximum height is 2.9 seconds, then the total air time of the ball would be 5.8 seconds. Why? Simply because you should know this as a concept in projectile that if the time going up to the maximum height is 2.9 seconds, it will also take 2.9 seconds for the ball to finally go down to the same height or to the same level, okay? So that is because along y-axis, you have the same influence, is the gravity acting all throughout, going up and down in the case of the case 2 projectile, okay? So again, if the time going up is 2.9 seconds, the time it takes to go down is also 2.9 seconds. Therefore, the total air time of the ball or the projectile is 5.8 seconds. You just basically double this 2.9 seconds, okay? Miss, why are you noting down the total air time, which is 5.8 seconds? Can't we just use this given? Well, if you are concerned with the range of the ball, that is the total horizontal displacement. So if you are solving for the total horizontal displacement or range, which is from here up to this point, the time that you should also use should also cover this point up to this point. And 2.9 seconds is only from this point up to this point, right? So you need to double it to get the total air time, which you can apply to finally get the horizontal distance within 5.8 seconds of air time, okay? So it's that simple. If you use 2.9 seconds, you're only gonna have or gonna get half of the range. So later, you're gonna have to double that, for example. But right now, I want the total air time as soon as possible. So whatever I get for d sub x, that's the range, okay? So let's plug in. So again, v sub x is still 20.4 meters per second. So v sub x is constant throughout the entire trip. And then the time it takes to cover the maximum horizontal displacement, aka range, is 5.8 seconds. Then you do that in your calculator. You're supposed to get 118.32 meters. Now take note, in multiplication, we follow the given with the least number of significant figures. So this is 3 significant figures. This has 2 significant figures. So our final answer should have 2 significant figures. So this will become 1.2 times 10 raised to the second power meters. Okay, so we just use scientific notation so that it will be easier for us to express this value in 2 significant figures. So that's our final answer for the range. Now take note, there is an alternative solution to this problem considering that we know the initial velocity as well as the launching angle or angle of projection that we call. So that's the horizontal displacement or range, but the alternative solution would be this. So, Miss, where did you get that formula? I'm gonna try my best to create a separate video explaining where it went, but your teacher has probably shown you this, or perhaps I'm just gonna link down a reference in this YouTube video's description for you to know where it came from. But this equation, memorizing this equation may come in handy for you to quickly solve for the range without going through this longer method. So, that is only applicable if you know the initial velocity. And that's neither v sub x or v sub y. It's actually this. And then raise it to the second power and then sine. And then this is 2 times your launching angle or angle of projection, which is 54.3 degrees. And then take note that g is 9.8 meters per second squared. So it's just the magnitude of the acceleration due to gravity. So that's it. So again, I'm going to link down a reference for you to know where it came from in this YouTube video's description box. So for the range, you just plug in velocity is 35.0 meters per second upon launch, raised to 2, and then sine times twice the angle, which is 54.3 degrees, divided by 9.8. In your calculator, you're supposed to get 118.47 meters. If you're not getting the same answer in your calculator, let me know in the comment section so I can help you or ask you what you're doing with your calculator that might be causing the mistake. But this is what's supposed to appear in your calculator if you did it right. You might notice, Miss, why is it not the same as your first solution? Is one of these solutions wrong? No, not necessarily. It's just that we're using different variables in solving for the range in this kind of approach, and there's also this alternative solution with different variables involved, like theta, you have v, for example. So that is the reason why there is a discrepancy in terms of the decimal places. However, that's the beauty behind applying the rules of significant figures. Because looking at this solution, it tells us that our final answer should also have two significant figures. Because in division, we follow the given with the least number of sig fig, and that's 9.8. So 2 sig fig, your final answer here should also be 1.2 times 10 raised to 2 meters. So that has two significant figures. And if you compare that with our first solution, you can see they're just the same. So meaning to say, the implication of that is that there are some degree of uncertainty with these digits, that's why they're not the same, and in reality, you shouldn't take them too seriously because the discrepancy is just caused by computation errors that we did in the middle of these solutions, right? So that's why you should follow the sig fig rules to really see the correct answers or the most accurate answers, and it's 1.2 times 10 raised to 2 meters. That's why they're consistent in this case, because we followed the right number of significant figures. So that's it. That's the range of the ball. Does it look reasonable? Yeah, it's roughly 120 meters, and definitely a baseball field can accommodate this kind of range, most probably. Now, at this point, I'd like to explain how we come up with the units, because it says here meters. In here, it's easy to see why it's meters. But here, you might be wondering, Miss, where did you get meters? It's simple. So, if you look at the numerator, this is m over s raised to 2. So, that would be m squared over s squared, right? You're gonna raise m and s to the second power. So, it's m squared over s squared. And then no units here. And then here, meters per second squared. Now, in division, what you need to do is to get the reciprocal of the divisor and then proceed to multiplication. That's a grade school math. You might not remember, but that's it. If you are dividing these two expressions, you need to get the reciprocal of the divisor and then proceed to multiplication. So, after this m squared over s squared, you're supposed to multiply it with the reciprocal of the divisor, which is m over s squared. And the reciprocal of that is s squared over m. So, s squared over s squared, it will be cancelled, and then m squared over m. You're actually gonna have meters as the remaining expression. And that's how you get meters in your final answer. So that's it for letter C. That's the range of the ball. And again, yeah, it looks reasonable, so we don't need to question the answer. It doesn't look unrealistic. At this point in the problem, we're going to solve for letter D. So that's to determine the ball's velocity just before it hits the ground. So if this is the scenario, what we are solving for is actually this arrow. So it could represent the velocity of the ball just before it hits the ground. So again, take note, if that is the velocity we're aiming for, it has a horizontal component and it has a vertical component pointing downward, right? So that's what we are targeting. And just to maximize this view further, again, this is the vector representation of our target variable, the velocity before hitting the ground. So that's the required to find. And then it has a rightward horizontal component, which is 20.4 meters per second. Miss, wait, why did you use 20.4 meters per second for v sub x? Again, this is the v sub x we solved for earlier, I think as early as part A. And v sub x is constant throughout the entire trip of the object in the trajectory. So it's still 20.4 meters per second, even up to this point where the ball is about to hit the ground, okay? And then v sub y is pointing downward. Now, this vertical velocity, or what we can consider as our final vertical velocity, is actually not known in the problem. We've been dealing with vertical velocities earlier, but those are not applicable. So, example, this is initial. So, this is vertical velocity upon launch. There's also v sub y, 13.7 meters per second earlier, but that is at 1.50 seconds. So, that's not what we need as well. So, v sub y in here is actually not yet known. So, we don't know the vertical velocity at this point, and this is something that we need to solve for using kinematic equations. So yeah, let's deal with it, because for us to know v, we need to know v sub x, but it's already known.
and then v sub y. So let's deal with v sub y. Let's write down what we know in the problem. The best approach to solving for this is to consider only this part of the trajectory, the one going down, because we are concerned with the velocity before it hits the ground. So at this point, I want you to just analyze or consider this second half of the trajectory, where it starts with 0 vertical velocity and then it goes down. So the initial vertical velocity in this case is 0 meters. Wait, miss, where did you get that? Again, if this is what we are analyzing, the downward part, just so we could target the velocity upon hitting the ground, the initial vertical velocity is actually 0 because, again, at the maximum height of the projectile, the initial vertical velocity is actually 0. And we can consider it as initial if our analysis is this downward path. Okay? And then acceleration along y is negative 9.8 meters per second squared still. And then d sub y is negative 41 meters. Wait, miss, where did you get d sub y? It's not given in the problem. Yes, it's not given in the problem. But take note that earlier, we determined that the maximum height is actually 41 meters. So in the downward motion of the projectile, that d sub y is actually the same vertical velocity that it will cover. That's how high it went. That's how long it will also travel going down, obviously, right? But why is there a negative sign? Simply because this displacement is measured below the original point or position of the projectile that we are considering. So if this is the path we are following, then this vertical displacement, negative 41 meters, is actually below the starting point. So make it negative, okay? And then time is 2.9 seconds. Miss, where did you get that? So earlier, we determined that the time it takes to go up the trajectory to the maximum height is 2.9 seconds. It will take the same amount of time going down for the projectile if you are dealing with case 2 projectile. As long as these are equally high, time going up is the same as time going down because you still have the same influence going down. It's just still gravity bothering you, making you accelerate at negative 9.8 meters per second squared. So you will travel just as fast going up and going down. It's just that going up, you're slowing down, and then going down, you're speeding up because you're now in favor of gravity's direction. So time going down is 2.9 seconds, okay? And then again, v sub y is what we're solving for. We want to know this because we want to know the velocity before it hits the ground, which is this, okay? So let's solve for it. Means it looks like we have a complete set of given, like there's no missing variable. Yeah, it means that, because these are our y variables, right? It's all complete here. Attendance check, they're all here. However, so there's no restriction here. We just pick the equation that contains the required to find whatever we want. So if we look at the equations, I choose the first equation because it's the simplest one and v sub y is readily isolated, right? So that's the best equation to choose. So yeah, let's work on this. Let's clean this first. So that's our equation. Then, so v sub y is v naught y plus ayt. And then next, take note that initial vertical velocity is 0, so we can cancel this, and we're gonna have final vertical velocity equals acceleration times time. Then we plug in, so acceleration along y is negative 9.8 meters per second squared, and then time going down is 2.9 seconds. And then you're gonna get final vertical velocity equals negative 28.4 meters per second. Now, I want you to notice something. Okay. I want you to notice that the initial vertical velocity and final vertical velocity are actually the same in terms of magnitude. It's just that the final vertical velocity is negative because the projectile is now going down, right? So take note that that is always true as long as you are dealing with case 2 projectile. So case 2 meaning to say, it's launched at an angle and then the starting and end points of your projectile are equally high, okay? So the vertical, the initial and final vertical velocities are gonna have the same magnitude in case 2 projectiles, regardless of what it is. It's a baseball, it's a golf ball, or what, okay? So, miss, why is that so? Simply because if the object is going up, its velocity is decreasing by 9.8 meters per second every second. And then as it goes down, it picks up or it gains 9.8 meters per second every second. Meaning to say, whatever vertical velocity it loses going up, it gains it back on its way down at the same rate, 9.8 meters per second every second. So whatever initial vertical velocity you have, you will reach the same vertical velocity before hitting the ground, okay? It's just that the sign is negative because it is now pointed downward. The vertical velocity is now pointing downwards for like the second half of the trajectory. So at this point, we can now write v sub y, or final vertical velocity, to be negative 28.4 meters per second, and we can solve for the velocity here because it's actually determined by v sub x and v sub y that are both known in the problem. So yeah, let's solve for the magnitude of the final velocity of the ball before it hits the ground. So again, we're still gonna use the Pythagorean theorem because, as you can see, we have a right triangle here through our vector representation of our velocity values. And then, for us to isolate c, we need to make it we need to get the square root of both sides of the equation, and that will become c equals square root of a squared plus b squared. And this will become v equals square root of vx squared plus vy squared. Nothing bloody. What I did is I just replaced this Pythagorean theorem variables with actual velocity variables. So c, or the hypotenuse, is the longest side, so it's v, and then a and b are the two other legs, which are v sub y and v sub x in our problem, okay? And then substitution, so v sub x is 20.4 meters per second. It's constant throughout the problem. And then the v sub y before it hits the ground is negative 28.4 meters per second. Do not forget to square them, okay? And then if you do that in your calculator, you're supposed to get 35 meters per second for the final velocity. So this is now the value of this red arrow pointing like this. So that's the velocity before it hits the ground. But it's only the magnitude. We're also going to solve for the angle. So solving for the direction or the angle of the final velocity of the ball, what we have here is this right triangle. So we can consider this as our angle to be convenient with a problem solving part. So that's our theta, and then this is the opposite side, right? So this one, on the other hand, is the adjacent side. So we can use tangent function, opposite over adjacent, and specifically opposite side is v sub y, and then adjacent side is v sub x. However, to cancel tangent, we need to do an extra step, which is to multiply both sides of the equation by arctangent. Nothing bloody. The point is that if you want to cancel tangent in tangent theta, just multiply both sides of the equation by arctangent. So it's some kind of rule, okay? If you do that, you can cancel the tangent expression here. So it's like arctan times tan gets cancelled, and then theta equals arctangent times v sub y over v sub x. And then you plug in the given value. So v sub y is this is v sub x, and in your calculator, you are supposed to get negative 54.3 degrees below the positive x-axis. So, miss, where did you get the below the positive x-axis thing? I don't know how to do that, although I'm coming up with this angle. So, the reason being is because if this is your velocity that you are trying to solve for, this red arrow pointing this way, its tail is actually in here. So, this is the origin point of your imaginary Cartesian coordinate system. And then this would be your horizontal axis in your imaginary Cartesian plane. And in that case, what we actually report in this kind of problem is the angle that our vector arrow makes with the horizontal axis. So it's actually this one. This is what we are reporting. But Miss, what you solve is this angle, so how come you're now saying that what we're reporting is the one that touches the x-axis? Well, obviously, this angle as well as this angle are actually just equal. So in mathematics, you should know this one. And also, if you're gonna use this triangle, let me draw something. If you're gonna use this triangle to solve for the velocity, you're still gonna arrive at the same answer because your v sub y would still be the same if you mirror this, and then your v sub x would also still be the same. Okay, so but then we came up with this illustration earlier, so it's convenient to use this theta. But take note that you're still technically solving for the equivalent of the angle that touches the x-axis, which what these problems really are going for. So that's actually it. So the final answer is negative 54.3 degrees below the positive x-axis. I actually accept it even without the negative sign because the negative sign is just an additional confirmation that this is below the positive x-axis. But by just saying 54.3 degrees and then it says below the positive x-axis, that's already enough. I personally find this redundant when there's a negative sign and then it also says below the positive x-axis. But please do check with your teachers because these are just conventions or ways of expressing this direction. So that's it. Now, in the calculator, if you're wondering, Miss, how did you do this? I don't know how to do this in the calculator. What's arctan? So, it's simple. If this is the one that you're trying to input in your calculator, just press negative 28.4 followed by the division sign and then 20.4, the denominator. Press equal sign and then shift or second function in your calculator and then press tangent, which appears as tan, and then press equal sign. So theta equals negative 54.3 degrees, and then just add the above or negative positive x, above or below positive x-axis thing, depending on the scenario that you are analyzing. So again, the final answer for this problem is 35 meters per second, negative 54.3 degrees below the positive x-axis. So that's our velocity for the ball before it hits the ground. Now, I want you to notice something. That velocity is actually also our initial velocity, right? So, at the start of the trajectory, the ball moves at 35.0 meters per second in that curved path. And the angle of projection is 54.3 degrees. And you got the same answer except that the angle appeared to be negative. So, that's actually a conceptual approach to doing that. Whatever is the initial velocity given, including the angle and the magnitude, or direction and magnitude, it's also the final velocity of that projectile before it hits the ground. I'm only referring to case 2 projectile, meaning to say the start and end point should be equally high. If that's not the case, then it won't be true, okay? But whenever this is the case, the initial velocity is gonna be the same with this one and then this, okay? But why is that so? Again, yes, as I mentioned, they're the same. You can see the magnitude as well as the direction. But the reason behind that is, again, if you have an initial vertical velocity, for example, which is 30 meters per second, again, initial vertical velocity, okay? What happens when the object is going up is that that vertical velocity will decrease by 10 meters per second every seconds, approximately, okay? It's exactly 9.8, but for simplicity purposes, I'm gonna use 10 instead of 9.8, okay? So again, that is because of gravity. So gravity is opposing this vertical velocity. So going up, this 30 meters per second will decrease by roughly 10 meters per second every second, meaning to say, after 3 seconds, this 30 meters per second will become 0 meters per second because it's decreasing by 10 meters per second every second. So at the maximum height, the vertical velocity is 0 meters per second. However, again, gravity is still acting at the maximum height. So going down, of course, the object will go back down because of gravity, right? So going back down, what happens is that the vertical velocity increases by 10 meters per second every second because gravity and velocity are now in the same direction. So you're going down and gravity is also pulling downward. So you're going to speed up in that case. Or I mean, the projectile is going to speed up in that case. So from 0 meters per second, it's again, it will then pick up 10 meters per second every second until it reaches 30 meters per second again. Because going up, if it took 3 seconds, it will also take 3 seconds going down, right? So, and then 3 seconds of picking up 10 meters per second every second will make you gain 30 meters per second as the final vertical velocity. Miss, why is there a negative sign? Now, simply because the vertical velocity is pointing downward in here. Okay? Now, given that case, if you think about it, since you're solving for your velocity, you're gonna use v sub y and v sub x. And if v sub y, well, because v sub x is constant throughout the entire trajectory, and if you look at v sub y, they also have the same magnitude from in the start and end position. So it means to say that you're always gonna get the same velocity from the start and then at the end position of your projectile. So that's actually it. So whatever velocity you lose going up, you pick it up going back down. So the start and end will give you or will have the same vertical velocity. And considering that v sub x is also constant, then v itself, which depends on v sub y and v sub x, will be of the same value from here and then here. Next, what about the angle? Miss, I just noticed that the angle is 54.3 degrees positive upon launch, but before it hits the ground, it's negative 54.3 degrees. So why is that so? Well, simply because upon launch, your velocity points this way, right? And then that's v, so it has an x component, y component, and then this is your horizontal axis in your imaginary Cartesian plane, because that's where the origin is. That's the tail of your main vector, okay? And the theta you're dealing with is this. So as you can see, if you look at this, it's actually above this horizontal axis. So this really comes out as positive, which signifies that that angle, or theta, is above the horizontal axis. And then for the time when the velocity is, or when the projectile is going down, the velocity is actually pointing like this, because this is the part of trajectory it's describing. And then, of course, it has an x component, it has a y component pointing down, and then the angle that we measure, because this is the triangle that we have, is actually this, right? However, by convention, we report the angle that is closest to the horizontal axis of the imaginary Cartesian plane. So if this is your main vector pointing like this is the tail, so that's the origin of the Cartesian plane. This is the horizontal axis of your Cartesian plane. And the angle closest to that is actually this. So this is what we are reporting when we report the final velocity before it hits the ground. And as you can see, this angle is actually below the x-axis, or below the positive x-axis. That is why it comes out as negative. And that's why we also say below the positive x-axis, because we're actually referring to this. And again, there's no harm in solving for this because they are equal mathematically. You should know that because of trigonometry, right? So yeah, that's it. That's actually for it for this problem. Again, you can solve for letter D mathematically like I've shown previously. And then this is a conceptual approach to this part of the problem. Depending on your teacher, maybe the teacher just wants you to like justify or explain it conceptually. But then if they ask you for a some sort of mathematical proof, then you can go back to what I showed you earlier, which is actually this. Yeah, but either way, the point is that you should know how to answer or justify whatever answer that you will give, whether it's mathematical or conceptual. So that's all for this video. Thank you so much and have a great day.